Okay, so welcome to this next video in the playlist on group theory. In this video, what we're going to do is discuss the concept of a group isomorphism. Okay, right. So the way I'm going to do this is I'm going to firstly go over the concept of what it means for two groups to be isomorphic. So I'm going to show you two groups that are isomorphic, and hopefully you might be able to get the idea of what this is actually all about. Then we'll actually go through what isomorphic means, and then we'll go through what a group isomorphism is. Okay, then what I'll do is I'll show you that not all groups of the same order are isomorphic, and I'll give you an example with groups of order 4. Okay, and then I'll show you what, in my opinion, was the first great deep, meaningful result that group theory taught me when I was first learning it, okay, which is that the real numbers under addition is actually isomorphic to the positive real numbers under multiplication, which I think is a very, very deep result. Okay, so we'll have a look at that. Right, okay, so let me firstly then draw you out two groups that are isomorphic to one another, and hopefully you might be able to get what the idea of two groups being isomorphic actually is. Okay, right, so the first group that I'm going to show you is one that we've already covered in previous videos, okay, which is the symmetric group of two elements, okay, so S2. Okay, so remember, the way that you think of S2, the way that you think of building S2 is you take the set containing two elements, okay, so we'll have the set containing the symbols 1 and 2, okay, and you think about all of these set permutations of this set containing these two elements, okay, and what we're going to do is we're going to give these set permutations symbols, we're going to give them names, and then we're going to put these symbols into a set by themselves and define a composition law on them to create a group, basically. Okay, right, so let's think about all the set permutations of this set containing just two elements. Okay, well, one of the set permutations that exists is just the identity permutation, which maps all elements onto themselves. So we'll call this set permutation by the symbol I for identity map. Okay, and then the only other set permutation that exists of this set of two elements is the one which swaps the two elements over. Okay, so it will map 1 onto 2 and 2 onto 1. Okay, and we'll call that set permutation tau. Okay, for transposition, that's common notation for transposition. Okay, right, so then to create the group S2, what we do is we stick these two symbols, I and tau, into a set together. So here is I and here is tau. Okay, now they're in this set, so let's just colour code them in. So here's tau in blue, and here's the identity in orange here. Okay, and now what we need to do is define a composition law on the elements of this set, basically, to turn it into a group. Okay, so I'll do this here. So we need to define what all compositions are. So I'll give each of the elements a column, like so. So here's the identity and here's the tau, columns here. And I'll give every element a row here. And then what I'll go and do is define what the composition of all of these elements with one another is. So every possible composition is. And all I need to do now is fill in the entries of this table. Okay, now, the way then that we can ensure that this is actually going to form a group, this composition law is actually going to form a group, is to think of the composition of these symbols as meaning the composition of the set permutations which we've thought of these symbols as representing. Okay, so when I say x composed with y, where x and y are variables, they can be any one of these symbols. Okay, that means do the set permutation y first, and then do the set permutation represented by x, and then get the net set permutation, and then whatever symbol represents that net set permutation, that's going to be the answer in our composition table, basically. Okay, right, so we know that the identity composed with the identity, that just means do this twice. Of course, the net thing that we get there is just going to be the identity, because if you send 1 to 1 and 2 to 2 and then do that twice, then the overall map is still just the identity map. Okay, if we do I composed with tau, that will mean do tau first and then do I. Okay, so we'll swap them over and then just keep them the same. So that's overall is just tau again, okay? If we do tau composed with I, that means do the identity first, i.e. do nothing, and then do tau, so swap them over. The net result of that is that you swap them over, okay? And then tau composed with tau, the final entry here, means do tau twice, so swap them over and then swap them over again, and that means overall we swap them back. So overall that net set permutation is just the identity. Okay, and this actually forms a group, and in previous videos we've discussed why that forms a group. Okay, because it obeys all of the axioms of group theory, basically, which, remember, are number one, the composition law needs to be closed. Well, it's certainly closed. All of the answers here are back in here, so all of the entries here are symbols from our set. Okay, so it's closed. It will obey associativity because of the way that we thought of these symbols as representing set permutations and the composition of the symbols as representing the composition of these maps. Okay, we do have an identity element, that's the symbol that's representing the identity map. Okay, and all of these symbols do have inverse elements because I is its own inverse. If you compose I with I, it gives you I, and tau is also its own inverse. If you compose tau with tau, it also gives the identity element. Okay, so it is a group, basically. Okay, so there's one group. Now what I'm going to do is I'm going to show you another group, a different group, okay, but this other group is going to be isomorphic to this one here, okay, and I want you to hopefully see from me drawing this out, maybe what the concept of isomorphic is, okay, and then we'll go through it. Right, okay, so I'm going to have my other group here, and I might call this G prime over here. Okay, so I might call this one over here G for now, just G for group, basically. It is S2, but we'll call that one G, and we'll call this one G prime. That's helpful later for when we want to write out more generally what an isomorphism is. Okay, right, so G prime. So what I'm going to do is I'm going to start by creating the set, and then I'm going to define a composition law on the set. So this set is going to contain two elements again. It's going to have the symbol +1, and it's also going to have the symbol -1. Okay, so here's my set of symbols for this group. Now I need to define a composition law on this. Okay, and the composition law I'm going to use is actually multiplication. Okay, so I'm going to call the composition here multiplication. Okay, and I'm going to define what all of these, all combinations of elements multiplied with one another is. So, +1 times +1, I'm going to define that to be +1, and I'm just defining this in line with our normal notion of multiplication of these symbols. Okay, +1 times -1, I'm going to define that to be -1. -1 times +1, I'll define that to be -1, and -1 times -1, I'll define that to be +1. Okay, now that does form a group. G prime is a group. It's a set of symbols with a composition law defined on it, and this composition law does obey the axioms of group theory. Okay, so I've got these two different groups here. Now have a look at them. Okay, are they really that different? Okay, look at these composition tables. Do they really look that different? These two groups here, G and G prime, they are isomorphic to one another. Okay, and the way that we often write isomorphic is we'll say that G is wiggly equals G prime. Okay, so this should be read as G is isomorphic to G prime. So what do I mean by isomorphic? Okay, well basically what it means to say that this group is isomorphic to this group is that all that you have actually done to change this group into this group is change the symbols that you're using. Okay, so by relabeling up the symbols, I can turn this group G into this group G prime. So what I mean by that is if I rename my composition here, if I turn it from being abstract composition like so, and I rename it multiplication like so, okay, that's one of the renamings that I need to do. So let's just do these renamings as I'm talking about them. So we're going to rename our composition law as multiplication here, okay? In addition, if I relabel up these symbols, if I say, okay, let's turn this I symbol into +1. Okay, and I should have just stressed, +1 is the identity element over here. Hopefully that's pretty obvious because it composes with any other element on either side to give back those other elements. Okay, so if I now change my identity element here to being the symbol for the identity element here, okay, then what I'm going to do is I'm going to replace it everywhere in this composition table with +1. So all I'm going to do now is relabel up I as +1. So just wherever you see I in this composition table, replace it with +1 here. Okay, so I've just relabeled up all of those i's as +1s, and now if I relabel tau, if I change the symbol I'm using from tau to -1, I'll just relabel up all of the entries in this composition table now that are tau as -1. What do I end up with here? I have turned it into this. That's exactly the same composition table as I've got over there. So just by changing the symbols that I am using to represent the elements of this group, I can turn this group, this composition table of this group here, into the composition table over here. Okay, that is what is meant by isomorphic. Okay, well, if two groups are isomorphic, then you can relabel up the composition and all the elements of the group, and if you do this relabeling to the composition table, it will turn it into the composition table of the other group that you're claiming it's isomorphic to. Okay, that is what is meant by isomorphic. It really means that these two groups that I have got here, they're not actually that different at all. They are capturing the exact same algebraic structure. All I am using is different symbols for my algebraic structure over here than what I'm using over here. Okay, there is no more truth in this one than this one. I'm not going to suddenly be able to find something new in one of these compared to the other, basically. So if I study this algebraic structure here and find loads of amazing properties that it might obey, and they're all going to apply to this one as well, because all I have literally done is just change the symbols I'm using, basically. The algebraic structure is actually the same. That is the concept of a group isomorphism, that the group algebra structure is the same. All that you've done is changed the symbols. Okay, right, so now let's explore what the concept of a group isomorphism is. So I've told you now what it means for two groups to be isomorphic to one another, and I'll just write that keyword out. Okay, so we would say that G and G prime are isomorphic to one another, and you can denote that as wiggly equals, like so. Okay, right. What then is the concept of an isomorphism? Okay, well, basically, if you want to show that two groups are isomorphic to one another, what you need to do is show that there is an isomorphism between them. Okay, now what then is an isomorphism? Well, an isomorphism is this relabelling function, basically. Okay, I've said that if I want to show this one is isomorphic to this one, I need to find a way of relabeling up the elements here in this group to turn the composition table of this group into the composition table of this other group that I want to show that it's isomorphic to. The isomorphism is this relabeling function, basically. Okay, so in this case, what was my isomorphism? Okay, and isomorphisms are often denoted lowercase phi, like so, but you can use other symbols for them, and they are a function, basically, which maps my group G here onto my group G prime. Okay, and this function needs to be a bijection. It needs to take every element here onto an element here, and every element here has to have only one element from here being mapped onto it. Okay, and every element here has to have one mapping onto it. So it needs to be injective and surjective, so it needs to be bijective. Okay, right, so an isomorphism, phi is the isomorphism here, okay, will map G onto G prime, and basically it's this relabeling function. It's going to take every element in our first group here, and it's going to relabel it up with a new element in our second group, G prime here. Okay, so in this case, what was my isomorphism? I told you what my isomorphism was, even though I didn't use that terminology. I said let's relabel I with +1, and let's relabel tau with -1. Okay, that was my isomorphism in this case. So if I draw this out even better, okay, let's have our group G here represented crudely as a little set here. Okay, and let's have my other group G prime over here with the two symbols +1 and -1 on. Then my isomorphism in this case is just this mapping. This is my isomorphism, this relabelling function that maps all the elements in G onto an element in G prime, okay, and it's a bijection, okay, so it's one-to-one and it's surjective, okay, so that it really is just a relabelling, basically. You are taking every symbol here and you're turning it into a symbol in G prime, basically. Okay, right, so that is what the isomorphism is. It is this relabelling map, basically, that takes all the elements in your first group, G, and relabels them with an element in your second group, G prime. Okay, now, that's lovely, okay? We've got a relabelling map, but of course, if the two groups are really going to be isomorphic, there has to be more conditions on phi than it just being a relabelling map. Okay, because we need to capture somehow in our definition of an isomorphism the fact that when you actually turn this, when you actually relabel up the composition table in your first group using the isomorphism, okay, or this mapping, because we haven't yet fully defined it as an isomorphism yet. Okay, so all we've got at the moment is a relabelling map. For it to become an isomorphism, we need to capture the condition, which is that when you relabel the composition table using this relabelling map, as I did here, okay, that this actually becomes the composition table of your new group. We need to somehow capture that concept, okay, because that's what we really mean by isomorphic. Okay, we don't just want a relabelling map. I could create you relabelling maps for groups that weren't isomorphic. We need that when we relabel the composition table in our first group with the relabelling map, that it turns it into the composition table of my second group, basically. Okay, right. So how do we capture that concept then? How do we capture that concept? Okay, well basically what I am saying is that if I act phi, if I use phi on any one of the entries in this composition table, it has to give the answer, or the analogous answer, in my composition table over here. So what does that actually mean? Well, let's say I have an arbitrary term in my composition table, and I'm going to go more general now. Okay, so we're going to step away from these examples here, because this is a bit too simple, because they're groups of size 2. Okay, I'm going to go a bit more general now. So let's say we have more generally just two groups, G and G prime, and we want to show that they're isomorphic to one another, and these could be much bigger than two elements, basically. Okay, right, so let me draw out the composition table of G. So what we want to prove is that if we have any entry in our composition table of G, okay, which we'll call X composed with Y here, so X and Y are arbitrary elements of big G, okay, and here is an arbitrary element therefore of the composition table, we want to prove that when we use this relabelling map on X composed with Y, okay, so what I'm saying is go through all the different entries of the composition table and map them onto what they will be mapped onto under this relabelling map, which we want to be an isomorphism. That needs to be the analogous term in G prime. Now, what's the analogous term in G prime? Well, let me just put the composition table of G prime up here. Okay, well, what is the analogous term in G prime? Well, X and Y, what are they going to be mapped onto in G prime? They're going to be mapped onto phi of X and phi of Y. Okay, so the analogous entry in the composition table of G prime is phi of X composed with phi of Y, where this composition is in the composition table of G prime. So let me just put a bit of colour onto this. Okay, so here is our composition table for the for the group big G. Okay, I am now saying take an arbitrary element little x and an arbitrary element little y, okay, and the entry in the composition table, x composed with little y, is then just an arbitrary element in this composition table, an arbitrary entry. Okay, so I'm keeping this completely general. I'm now saying if we map that onto what it will be relabeled as under our relabelling map here. Okay, just like we did here, basically, for all of these elements, we relabeled them with this relabelling map here. Okay, I'm now saying relabel that with our relabelling map, which we are claiming is going to be an isomorphism. Then if it is going to be an isomorphism, that better turn this into the analogous entry in my composition table over here. Now, what is my analogous entry in my composition table over here? Well, we know that little x is mapped onto phi of little x, and little y is mapped onto phi of little y, okay? And in the composition table over here, then, phi of little x composed with phi of little y is going to be the answer. So we want these two things to be equal to each other for all little x and y is an element of big G, basically. Okay, so we want phi of x composed with y to equal phi of x composed with phi of y. Okay, for all little x and little y is an element of big G. Okay, and that is the condition on this relabelling bijective map between G and G prime to be an isomorphism, basically. Okay, so to put all of this together then, two groups, G and G prime, will be isomorphic if there exists a mapping phi which maps G onto G prime, okay, where phi is bijective, okay, so it needs to be injective and surjective, and phi of x composed with y is equal to phi of x composed with phi of y for all little x and little y is an element of big G, basically. That is the way you will see the condition for two groups to be isomorphic written, and that is the definition of an isomorphism, a map that obeys all of that, basically, a phi that obeys all of that. Okay, so if there is an isomorphism between two groups, then the two groups are isomorphic, basically. Okay, right, so as I say, just think of this condition here as meaning when I relabel up the composition table in my first group, using this map phi, it has to turn the composition table into what the composition table is over here, basically. That is what this term, well, that's what this condition says, basically. Okay, that's what it's capturing. It may look complicated, but that's all it is really saying. Okay. Right, so we'll call it there for this video, and in the next video what I'll do is I'll discuss this a bit more at the start, okay? So we'll see, for instance, things like the fact that the identity is always mapped onto the identity by any isomorphism. And then what I want to do is I want to show you that two groups of the same order are not necessarily isomorphic. I'll use examples of groups of order 4 to do that, because at the moment I've shown you two groups of order 2, okay, that are isomorphic to one another. So you might be now starting to think that maybe all groups of the same order are isomorphic to one another, which is not true. Okay, so I want to show you two groups of order 4 that are definitely not isomorphic to one another, that you cannot find an isomorphism mapping between them. Okay, and then after that what I'll do is briefly discuss the concept of an isomorphism class, and then we'll go on to this deep result that impressed me, at least when I first learnt it, which is that the real numbers under addition, the group of real numbers under addition, is isomorphic to the group of positive real numbers under multiplication.